You are sitting at home late at night, suddenly you feel uneasy, maybe a little fever, maybe some stomach pain. The hospital is far, your doctor isn't picking up the phone, and Google is just giving you 10 different answers that make you even more worried. What if, in that very moment, you had a trusted friend who could ask you the right questions, understand your symptoms, and guide you with care? That's exactly why we built this AI powered healthcare chatbot. It is not just a keyword based program, it actually tries to talk to you and ask follow up questions and give you useful advice while reminding you to take care of yourself. In today's video, I am going to walk you through how this chatbot works, the technology behind it, and how it can actually make healthcare support more accessible for everyone. So, I type in my symptoms. I have fever, a bit of headache, and red spots over my body, along with itching and abdominal pain. The chatbot immediately gets to work. It uses a symptom extractor, which is like a digital detective. It scans my sentence, pick out the key symptoms like fever, headache, itching, abdominal pain, and maps them to its medical database. But here's the clever part, it doesn't just stop there. The bot knows these symptoms could point to multiple conditions, so it starts asking me guided questions. Have the red spots been spreading over the last few days? Do you feel any unusual tiredness or dizziness? Have you noticed scaling or skin irritation around the red patch? These questions act like a real doctor probing deeper. They help separate between a viral fever, an allergic reaction, or a fungal infection. After I answer this follow up, the chatbot runs everything through its trained random forest model. It processes my symptoms, cross check with thousands of patterns in the dataset, and finally says, based on your answers, you may have fungal infection with a confidence of 82%. That's not just a random guess, it is data backed probability, giving me confidence that the system actually understands my condition. But the chatbot doesn't just give me a name, it educates me. It explains in humans, fungal infection can occur when an invading fungus takes over an area of the body and is too much for the immune system to handle. Fungi can live in air, water, soil, and plants. There are also some fungi that live naturally in human body. Like many microbes, there are helpful fungi and harmful fungi. In just few lines, I not only know what I might be facing, but also why it happens. And then comes the most practical part, the precautions. The chatbot suggests bath twice daily, use Dettol or neem in your bathing water, keep the infected area clean and dry, always wear fresh, clean clothes. Simple, doable steps that immediately make me feel that I am in control of the situation. And just when I think the conversation is done, the chatbot ends with a little note of empathy. A healthy outside starts from inside. That one line completely changes the tone from a robotic diagnosis to a human connection. It reminds me that health is not just about medicine, but also about self care, lifestyle, and positivity. So, in this example, the chatbot took a messy mix of symptoms fever, headache, red spots, itching, abdominal pain, turned it into a structured information, asking the right follow up questions, and then confidently guided me towards a possible fungal infection complete with the explanation, precaution, and even a motivational thought. This is the future of healthcare, where AI doesn't just replace doctors but act as the first line of guidance, reducing pain and empowering you with clarity. If you found this fascinating, make sure you stay tuned because in the next video we'll go behind the scenes and actually look at how AI model learns and improves with every conversation. Open VS Code and create a new Python file and then save it. Save it in the same folder where you have saved the raw data and then give it a name, let's say health chatbot, and then save it. Import RE. RE stands for regular expression. Think of it as our text search magnifying glass. We use RE to split text into words, find patterns, and handle fuzzy matching later. Import random. Tiny helper for variety. We use it to pick a random empathy code at the end so that the bot feels warm and human. Import pandas as PD. Pandas is very helpful to load CSVs, slice columns, and give us data frame tools. When we say pd.read CSV data, the pandas read the training data into memory. Import NumPy as NP. NumPy provides numeric arrays. We create the input vector for the model np.zeros and do fast numerical operations. Import CSV. Lower level CSV reader used for reading master files, description, severity, precautions. We could use pandas for this too, but the simple csv.reader works fine. From sklearn, import preprocessing. We use level encoder to transform textual disease levels into numbers the model can use. From sklearn.assemble, import random forest classifier. The model we choose, random forest. Later I will explain why this is a sensible choice for this kind of tabular symptom data. From sklearn.model selection, import train test split. Simple utility to split data into training and testing set. From diff live import get close matches. This is our easy fuzzy matching tool. If the user types a typo like fever, get close matches helps us to get fever. From fever, it will get fever. Import warnings and warnings.filter warnings ignore category equal to description warning. This suppresses the noise description warning so that the console stays readable. Note that do not blanket suppress the warnings in production. If you want a quick recap of what random forest classifier is, check out this step-by-step tutorial by Data Analytics Lab. Loading the data. Training equal to pd.read CSV. Data slash training.csv. Testing equal to pd.read CSV. Data slash testing.csv. We load two CSV files, training.csv and testing.csv. Training.csv contains the symptom columns, one column per symptom, typically 0 or 1, and a prognosis, the disease. Testing.csv is there for evaluation or secondary checks. If these files aren't found, Python throws file not found error. Always check for working directory. Cleaning duplicate column names. Sometimes CSVs contain duplicate columns. Pandas append .1, .2 to resolve duplicates when reading. For example, fluid overload and fluid overload .1, we strip the trailing .digit with a regex. .str.replace operates on column names, a panda index. After stripping, duplicates can reappear. Two columns both named fluid overload. That would break the model or feature indexing. So we call training equal to training.loc, training.columns.duplicate. This keeps only the first occurrence and drop duplicate columns. The wave-like function negates the Boolean mask. Why is this important? If training data and the later columns list disagree on features, you will get index errors when mapping the tree nodes. Earlier in your debugging, you saw index error index equals to 133 out of bounds for axis 0 with size 132. This fix prevents the mismatch. We are making sure the cast list has unique names before the shown beginnings. Split features and label. Training.column -1 assumes the last column is prognosis. So we take all columns except the last as feature. Those are symptom flags. X equal to training columns and Y equal to training prognosis. X becomes the data frame of features, symptom columns. Y is the series of labels, disease names. Important assumption is that your CSP must have the prognosis column at the end. If not, adjust. For example, fever equal to 1, cough equal to 0, sore throat equals to 1, prognosis equal to flu. Level encoding, translating disease name to numbers. LE equal to preprocessing dot level encoder, Y equal to LE dot fit transform Y. Machine learning models want numbers, not strings. Label encoder give each disease a unique integer. For example, cold, flu, migraine equal to 0, 1, 2. LE.fit transform Y learns the mapping and transforms Y into encoded integers. Later, when we predict class 2, we use LE.inverse transform 2 to get migraine back. We will see that in the prediction routine. Train test split. X train comma X test Y train comma Y test equal to train test split X comma Y comma test size equal to 0.33, random state equal to 42. We split data into training and testing set. Test size equal to 0.33, 33% reserved for testing. Random state equal to 42, deterministic split, so results are reproducible. 42% is the mean, but it's practical. This helps us evaluate the model later and avoid training on all the data. The analogy is that training on the practice problem and then evaluate on the test set. Choosing and training the model. Model equal to random forest classifier. N estimators equal to 300. Random state equal to 42. Model.fit X train comma Y train. Random forest classifier is an assemble of decision tree. Each tree learns different splits. The forest votes. N estimators equal to 300 means 300 trees. More trees often increase the stability at the cost of compute. For symptom disease classification, random forests are very practical. They handle sparse, high dimensionality binary features well, are robust to noise, and give predictive probability for confidence. Model.fit X train, Y train trains the forest on the data. This is where the model learns how symptom combinations map to disease. Dictionary, severity dictionary, description list, and precaution dictionary are containers we fill by reading the master CSV files. They hold human readable descriptions and numeric severity scores for symptom. Symptoms dictionary maps symptom column names keys to the index in the X data frame. Example, fever 0, cough 1. This mapping is used when we build the input vector for the model. Why keep these master files? They allow the chatbot not only to predict a disease but also to explain it, description, and give suggestive precaution. Loading, description, severity, and precaution. Def get description with open master data symptom description.csv as CSV file for row in csv.reader CSV file description list row 0 equal to row 1. Def get severity dictionary with open master data symptom severity.csv as CSV file for row in csv.reader CSV file try severity dictionary row 0 equal to in row 1, except pass def get precautionary dictionary with open master data symptom precaution.csv as CSV file for row in csv.reader CSV file precaution dictionary row 0 equal to row 1, comma row 2, comma row 3, comma row 4. What is happening over here is that get description read CSV where each row maps symptom disease name to a human readable description. It populates description list so later description list disease returns a paragraph. Get severity dictionary opens a CSV giving each symptom a severity score, an integer. We try and accept because some rows may be malfunction. Get precautionary dictionary reads precaution suggestion each disease maps to a list of precaution strings. These functions are called at the start of the chatbot to fill the dictionaries so that the bot can explain and advise. Think of these as the bot's knowledge base, factual text that helps it to be more helpful and human. Symptom Extractor symptom synonymous equal to stomachache, stomach pain. If the user writes stomachache or stomach pain, it would mean the same. Def extract symptoms user input all symptoms extracted text equal to user input dot lower replace synonymous replacement for phrase mapped in symptoms synonymous dot item if phrase in text extracted dot append mapped exact match for symptom in all symptoms if symptom dot replace in text extracted dot append symptom Fuzzy match. Words equal to re dot find all comma text. For word in words, close equal to get close matches word s dot replace. For s in all symptoms, n equal to 1, cutoff equal to 0.8. If close, for sym in all symptoms, if sym dot replace equal to close 0, extracted dot append sym. Return list set extracted. So what is happening over here is that our goal is to convert user sentences free text into standardized symptom tokens that match dataset columns. Step 0 is to normalize text equal to user input dot lower, replace lowercase everything and replace hyphens with spaces so matching is stable. Step 1 is synonymous. Iterate through symptom synonymous if phrase stomachache appears in the text, we append stomach pain, the dataset column. This catches common multi-word expression. Step 2 would be exact matches. For every column name in all symptoms, we convert underscores to spaces and check if the sore throat in text. This catches user writing exactly similar words. Step 3 fuzzy matching. Split text into words with re.findAll, comma text. This extracts tokens like I have fever and cough. For each token, get close matches find a close symptom phrase among candidates. The symptom name with spaces. If a close match is found above cutoff 0.8, we map back to the underscore from and append. This handle typos like fever, FEAVER to FEVER. Finally, list set extracted returns unique items and remove duplicates. This three pass approach balances the precision, exact matches, recall synonymous phrase, and robustness, fuzzy typos. Prediction function. Def predict disease symptoms list input vector equal to np dot zeros length Symptoms dictionary for symptom in symptoms list. If symptom in symptoms dictionary input vector symptoms dictionary symptom equal to 1, prediction probability equal to model dot predict probability int vector 0, predict class equal to np dot aggregated max prediction probability disease equal to le dot inverse transform predict class 0 confidence equals to round predict probability predict class multiplied by 100 round off to 2 return disease confidence and prediction probability. So what is happening over here is that we must convert the list of detected symptoms into the model for input format a numeric vector the same length as columns. Input vector equal to np dot zeros length symptoms dictionary initial vector when where very symptoms is 0 absent for each symptom present we set the corresponding index to 1. Example, if fever is index 2 input vector 2 equal to 1, we call model dot predict probability input vector which returns probability estimates for every class disease. We take 0 to get the array for the single input. Predict class equal to np dot aggregated max predict probability. Select the class index with highest probability. Disease equal to le dot inverse transform predict class 0 maps back to the disease name. Confidence equals to round predict probability predict class multiplied by 100 round off to 2 turns the probability into a percentage with two decimals. We return disease, confidence, and prediction probability. Full vector includes the possible letter use. Empathy quotes. Quotes like health is wealth, take care of yourself. These are short messages that the bot can pick randomly to end on a caring note. A machine that closes the conversation gently feels friendlier. The chatbot. Now we'll walk through the main function step by step. Def chatbot get severity dictionary, get description, get precaution dictionary. On the start, the bot loads the master files into the dictionaries so that it can explain and advise. This ensures description list, severity dictionary, and precaution dictionaries are available. In the next block, we are greeting and some basic info. Print hello to healthcare chatbot. Print hello. Please answer a few questions so I can understand your condition better. Name equal to input. What is your name? Age equal to input. Please enter your age. Gender equals to input. What is your gender? Male or female or other? Explain. Simple user onboarding. Name, age, gender. This could be used later for risk adjustment. Old age risk are higher. Initial symptom input would be symptoms input equal to input Describe your symptoms in a sentence. For example, I have a fever and stomachache. Symptom list equal to extract symptoms, symptoms input, comma columns. If not symptom list, print, sorry, I could not detect valid symptoms. Please try again with more details. Return, print, detected symptoms, join symptom list. What is happening over here is that the user types anything, the extractor tries to map to known symptoms. If nothing matches, the bot politely asks to try again. This is a pragmatic fallback. Now collected context. Num days equal to int input for how many days have you had these symptoms. Severity scale int input on a scale of 1 to 10 how severe do you feel your condition is. Pre-exit input do you have any pre-existing condition like diabetes, hypertension. Lifestyle equal to input do you smoke, drink alcohol or have irregular sleep. Family equals to input any family history of similar illness. Duration, num days, severity, subject scale, pre-existing condition, lifestyle, family history. This helps the bot judge urgency and could be used to modify prediction, risk scoring. In earlier versions, we used search answers to adjust probabilities. Initial model guess would be disease confidence probability equal to predict disease symptom list. Based on the current symptoms, the model returns its top guesses with a confidence. Now the clever part, disease-specific follow-ups. Print, let me ask you some more questions related to disease. Disease symptoms equal to list training, training prognosis equal to disease dot ILOC 0 minus 1 index, training prognosis equal to disease dot ILOC 0 minus 1 equal to 1. Now training prognosis equal to disease selects the rows in the training data frame where prognosis matches with the predicted disease. ILOC0 grabs the first matching row. There should be one representative row from reduced data or the max grouped row used earlier. Minus 1 removes the last column prognosis so we are left with symptom columns. Row equal to 1 selects the columns that have 1 in the representative row. These are symptoms strongly associated with the disease. Dot index extracts the index column names where the condition is true. List makes a Python list of those symptom names. We now have a list of disease specific symptoms we can ask about. For example, do you have nausea? If nausea is linked to guest disease, or alternative design note would be that this relies on the training set having representative rows per disease. Some datasets aggregate rows with dot group by max to get an indicative symptom vector. Guided question loop asked equal to 0 for SYM in disease symptoms if SYM not in symptom list and asked less than 8. Answer equal to input. Do you also have SYM dot replace yes or no? Strip dot lower. If answer equal to yes, symptom list dot append SYM asked equal to 1. Then we will iterate disease specific symptoms and ask up 8 yes or no questions to refine the input. If user answers yes, we append the symptom to the symptom list. This helps the model get richer input and usually improves confidence dramatically. Final prediction and reporting. Disease, confidence, probability equal to predict disease symptom list, print result, print based on your answers you have this specific disease, print confidence equals to confidence percentage, print about description list get disease, no description available. We rerun the predict disease with the updated symptoms, the output is predicted with confidence and a human readable description from the list. Description list dot get disease, comma, no description available safely returns a default if no description is found. Precaution and sign off. If disease in precaution dictionary, print suggest precautions for eye Predict in enumerator precaution dictionary disease, 1, print fi, PRDC, print plus random choice codes, print thank you for using the bot, wishing you a good health. Name. What is happening over here is that if a precaution entry exists, print it as a numbered list, pick a random empathy code, and sign off politely. End of interaction. Then we'll run the bot if name equal to main chatbot. This checks if the script is run directly, not imported. If yes, it calls chatbot, starting the conversation, typically random.